Today we will be presenting our project, the WiFly, Wi-Fi-based localization using a particle filter. Our problem comes from IMU drift yielding poor results when integrated over long periods of time. On the left, you can see the integration of two sensors, a cheap and an expensive IMU. Even with the high-end IMUs, the sensor will drift in under a minute. On the right side, you can see actual data that we took integrating our sensor measurements that shows strong drift over short periods of time. Our solution is to use Wi-Fi signals in order to localize our drone given a fixed map. We know that Wi-Fi signals are readily available, cheap, and can be a very diverse sensor set, as seen in the below images, which show the relative signal strength of 3 separate routers. As you can see, each router produces a different map of the environment. For our simulation, we used ROS and RVIZ for simulation and visualization. The RSSI signals were generated in ROS using a propagation model with separate decay values for free and occupied space. And the drone state was represented in SE23 with rotations, positions, and velocities. And the motion model was derived using the integration of IMU signals. On the bottom left, you'll be able to see our state, which includes a 3x3 rotation matrix and a vector of velocities and positions in R3. On the right, you'll be able to see our motion model, where the barred values are bias-corrected terms for rotational velocity and acceleration. Our particle filter uses an RSSI map, which is the relative signal strength of the Wi-Fi, in order to correct the current state. Particles are generated around a mean and propagated using the IMU integration model. After each integration, our particles are reweighted based on the error from the measured RSSI value and the current RSSI value in a given particle's position. From here, we resample if the effective particle weight gets too small. You can see our two algorithms for prediction and correction in the below images. Here, you can see our video. In the video, the red circle is the covariance of our particles, the blue line is the ground truth, and the teal line is the purely integrated IMU measurements. As you can see, our particles strongly track the ground truth value, whereas the integration of purely the IMU values drifts very far over time. This is supported in our simulation results, which show that the Wi-Fi-based correction methodology significantly outperforms the pure integration of sensor values. As you can see by our accumulated mean squared error, we are outperforming the integrated values by roughly an order of magnitude. Additionally, in the image on the right, you can see that the integrated values eventually return to the ground truth. This is actually because we were integrating a circle, and the circle came around at the end. Here, we can see the WiFly architecture. Our base layer is a Crazyflie 2.1 drone, which has an ESP8266 shield, along with an IMU and a display for the values. The ESP8266 is actually what is gathering our Wi-Fi data, and our payload was just enough so that we could hover. For the software architecture, we used a program that we wrote called WiFly Chat, which sets up a connection through a mobile hotspot with the drone's ESP8266 chip. Additionally, we set up a data stream that can call back the data, as you can see in the right image. It gives us a time, acceleration, gyroscope measurement, as well as the RSSI value at a given point. Next, we tracked the ground truth of the data using a Mocap system that was able to give us millimeter-level positions across a small environment. This allowed us to capture very high-fidelity data on where each Wi-Fi signal was being measured, so that we could later build a map. In this slide, we can see that the integration of the real-world data produces very noisy measurements. On the left side, and particularly small, you can see the blue circle that is the ground truth from the motion capture system. The teal line on the right, which diverges very quickly, is actually our integrated sensor value. As you can see, it needs correcting. There are also some particular limitations to overcome. The current WiFly payload of 14 grams only allows us to hover, and the flight time is limited to roughly 1 minute. Additionally, the particle filter can converge on an incorrect path, and increasing the number of particles does not particularly improve the particle convergence, but does increase the filter time. Additionally, we only used a 2D map, and as such, we're unable to localize in 3 dimensions. For our future work, we have a few plans, particularly building an RSSI map using the real-world data, allowing for 3D localization along the z-axis. Additionally, we want to work on some trajectory smoothing as we see some jumps in the particles when there are certain particles that fall out that have high probabilities. we would like to add 2 or more Wi-Fi routers and use other localization methods instead of a particle filter to see if we can get better convergence. Thank you for listening today, and we'll now open the floor to questions.